So, a very good evening, everyone. On the behalf of Buddha Group of Institutions and this ATAL FDP on remote sensing, I welcome you all for the day 4, and this is going to be the session 7. And this session will be taken by our esteemed speaker, Dr. Padamji Omar, Assistant Professor, Department of Civil Engineering, Babasaheb Bhimrao Ambedkar Central University, Lucknow. And the topic is remote sensing for monitoring land degradation and soil erosion. Before uh, before handing over this session to Dr. Padamji Omar, I would like to give a brief introduction of our esteemed speaker. Dr. Padamji Omar is an assistant professor in the Department of Civil Engineering, Babasaheb Bhimrao Ambedkar Central University, Lucknow, India. He obtained his BTech in Civil Engineering in 2012 and MTech in Geomatics Engineering from IIT Roorkee in 2014. He received his PhD from IIT BHU, Varanasi. Dr. Umar performs a broad spectrum of functions, not merely teaching but also at the forefront of cutting edge research. He has 10 years of experience in teaching and research. His research interests include remote sensing, GIS, groundwater modeling, and water resource engineering. His expertise has been recognized at the international and national level. He has guided undergraduate students in their major and minor projects. He has published more than 30 research papers in reputed international and national journals. He has presented his research at various international, 18, and national conferences at 14 places. He has made a significant contribution to 17 book chapters published by international publishers. He holds life membership of various national and international societies. He serves as a reviewer for several conferences, reputed journals, and academic encyclopedias. Dr. Omar also served as a guest editor for reputed journals, showcasing his impactful academic achievement. It is our honor and privilege to have Dr. Padamji Omar for this session. So, without wasting time, I will now invite Dr. Padamji Omar. Now, the platform is yours, sir. You can now start.
Good evening. Thank you, Ankur, for such a nice introduction. Good evening, everyone. I hope all are joined. Ankur, can we start?
Yes, sir, we can start now.
I think screen is visible to everyone.
Yes, sir.
Okay, great. So now we start. Good evening, everyone. It's an honor to be here today and to have opportunity to share my insights and thoughts on a topic that holds an immense significance for our Earth, that is remote sensing for monitoring land degradation and soil erosion. As many of you know that land degradation and soil erosion are pressing challenges that threaten food security, biodiversity, and sustainable development worldwide. As all of you know, these issues are not only critical for environmental scientists but also for policymakers, farmers, and communities who depend on healthy ecosystems. We try to make this presentation a little bit interactive, so you do not bore here. The question we face is how do we effectively monitor these changes in a world as fast and dynamic as ours? This is where remote sensing comes into play. As all of you know, what is remote sensing? Remote sensing it is just to sense the features या Earth's object without getting contact with that object or feature. So that remote sensing comes into play. A powerful remote sensing is a powerful tool that
Padam, sir.
allow us. Yes,
Padam,
yes.
sir. I'm sorry to interrupt you. Actually,
Okay.
sometimes your voice is breaking and it is coming from very far. So, if you can use headphone, it will be very audible to us and will be very clear to
Okay,
us.
just
Padam sir, are you there? Your voice is not coming, sir.
So now just what is remote sensing? Remote sensing is a powerful tool that allow us to see beyond that the naked eye. Our naked eye cannot see anything. That observe to understand the intricate processes affecting our landscapes. So remote sensing offers us as a bird's eye view of the earth, enabling us to monitor changes at a scale and precision that were unimaginable just a few decades ago. As all of you know, by leveraging this technology, we can identify hot spots of degradation, assess the effectiveness of conservation efforts, and plan for sustainable land management strategies. In this talk, what we learn, we can point out this. First, we understand the fundamentals of remote sensing and its applications in land monitoring. In the second step, we just know the key methodology for detecting and quantifying land degradation and soil erosion. In this presentation, I am taking a case study also of Sipra River Basin to just realize the real world examples where remote sensing has driven impactful change. And the last, you know what are the challenges and future directions in this field.
आपकी स्लाइड मूव
I
नहीं
hope
कर रही.
I hope this session not only informs you but also inspires you to think critically about how these technologies can be applied in your own work or research. I think all of our faculty, I encourage you to ask questions, share your perspectives, and discuss ideas during the question and answer session. Now let's begin. These are the outlines of my talk. Just first we let's discuss about the introduction. In the second step, we just know the what is remote sensing in GIS, and then we know the why land degradation is related to soil resource inventory, and then we study the case study of Sipra River Basin situated in the Madhya Pradesh, India, and what is the problem statement and objective of this study, and methodology and the results. So first we just know the introduction. Over the past few decades, the surface of the earth witnessed major changes in land use. These changes are likely to continue, driven by demographic pressure or by climate change. So therefore, monitoring tools are needed to monitor sustainable ecological status, improving soil conservation and water resource management. Floods, excess runoff, soil erosion, and related contamination and disequilibrium of the water cycle and other key issues that are controlled and influenced by soil characteristics. Conventional methods available in the literature, soil sampling and laboratory analysis cannot efficiently provide this information because they are slow, expensive, and could not retrieve all temporal and spatial variability. In this way, remote sensing has shown a high potential in soil characteristics retrieving in the last 3 decades. Then we know remote sensing provides us with a continuous, we repeated, continuous and constant source of information about the earth and its features, objects, and GIs are a methodology for handling all this geological data. This figure, as you saw on the screen, this figure shows the integration of remote sensing, GPS, this is GPS, my cursor is here, GPS, global positioning system, and geographic information system, GIS. This is the integration of these three technologies. It consists in components. First one is remote sensing. Remote sensing depicted with satellite imagery. This is satellite imagery, output of the sensors and satellite in orbited. This, this remote sensing represents the acquisition of information about the Earth's surface using sensors mounted on the satellites or aerial platforms. The imagery shows various features like land use and vegetation. These red color shows the vegetation part, and light red shows the field, open field area, and dark color shows the maybe water. The second component is of this figure is GPS, global positioning system. This GPS is a people using GPS devices in a field and a GPS device with navigation map. This highlights the role of GPS in determining precise geographic locations for mapping and navigation purposes. The third component of this figure is GIS, that is Geographic Information System. This GIS shows as a stack of layer maps. It demonstrates the system's ability to integrate, analyze, and visualize spatial data from remote sensing and GIS. These 4 layers include thematic maps for land use, topography, and more. Overall, if we conclude this image, overall the figure emphasizes the synergy of these technologies in applications like environmental monitoring, urban planning, precision agriculture, etc. If we talk about in the next presentation, next slide, what is remote sensing technology? In simple language, we can define observing means yeah, sensing the object from a distance remotely, or it's the science of obtaining information of any object or area without being physical contact with that object. This in the second paragraph, the scientific means the actual definition of remote sensing is mentioned here. We can know that remote sensing is a non-conventional recording of information from the ultraviolet, visual, infrared, and microwave regions of the electromagnetic spectrum. Means in remote sensing, we emit some wavelength, range of wavelength rays from the sensors, and these electromagnetic spectrum bands go to the atmosphere, through the atmosphere, and interact with the object of the earth and get it back to the sensor. In this figure, we're trying to show the what is the remote sensing process and what are the components of the remote sensing. Nowadays, the field of remote sensing and GIS has become exciting and glamorous with rapidly expanding opportunities. Many organizations, institutes, and academic institutions spend large amounts of money on these fields. So here the question arises: why these fields are so important in recent years? The two main reasons are there behind this. Maybe first reason is maybe scientists, researchers, and students and even common people are showing great interest for better understanding of our environment. By environment, what we understand, we mean the geographic space of their study area and the events that take place there. If we want to talk in other words, we have come to realize that geographic space, along with the data describing it, is a part of our everyday world. Almost every decision we take is influenced by some fact of geography. The second reason may be the advancement in sophisticated space technology, which can provide large volume of spatial data along with declining cost of computer hardware and software, which can handle these data. And make remote sensing and GIS affordable to not only complex environmental special situation, but also affordable to an increasing wider audience. If we look in this figure, the A part component shows the energy source of illumination. This part, this component A. This is the first requirement of remote sensing is to have an energy source with which illuminates or provides electromagnetic energy to the target of interest. In this case, our target of interest is point C, that is the Earth feature. The second component is B component, that is radiation in the atmosphere. As the energy travels from its source is sun, from A part to C part to the target, it will come in contact with and interact with the atmosphere it passes through. This interaction will take place a second time as energy travels from the target to sensor. The third component of this remote sensing is C component. This is interaction with the target. Once the energy makes its way to the target through the atmosphere, means through the part B, it interacts with the target depending on the properties of both the target and the radiation. After interacting with the third component, that is C, this energy transmit to the again through the atmosphere to sensor D, that is recording of energy by the sensor. D part is recording of the energy by the sensor. Sensor is mounted on the satellite. Then after the energy has been scattered by or emitted from the target, require a sensor. This sensor is not in contact with the target to collect and record the electromagnetic spectrum. When sensor receives the scattered emitted energy from the target, that is C point, it transfers it to the E section. That is transmission, reception, and processing to E. The energy recorded by the sensor has to be transmitted often in electronic form to receiving and the processing station where the data are processed into an image. After this transmission, we get the satellite imagery. And the last, second last component is interpretation and analysis. That is the F component. In this, the processed image is interpreted visually. Means we try to identify what is this object or feature visually and not digitally or electronically to extract information about the target which was illuminated. And the last component of this remote sensing is application. When we get the imagery and we identify the information from that imagery, then the application part is come out. The final element of the remote sensing process is achieved when we apply the information. We have been able to extract from the imagery about the target in order to better understand it, reveal some new information or assist in solving a particular problem. In short, these seven components makes the remote sensing is a powerful tool in assessing the soil erosion or land degradation. Now come to this figure, that is the another example of remote sensing technology in the field of land degradation and soil erosion mapping. In this figure, you can see that this is the sun, it is the source of energy, the primary source of energy, emitting electromagnetic radiation that interacts with the earth surface. In this case, we take the earth surface is wheat field, where you can see the figure. Now the part B, this is the path radiance. This is the path radiance. So the radiation reflected from the earth surface and influenced by the atmospheric component. As I mentioned in the previous slides, that this component is this path radiance. Then this path radiance interaction with the earth surface after passing through the atmosphere, this energy interact with the earth surface. So in the diagram, so the wheat field reflecting solar radiation, which is then captured by satellite. In this case, I have taken the IRS satellite, Indian Remote Sensing Satellite. Indian Remote Sensing Satellite receives the reflected radiation. The satellite from the earth surface. When the satellite collect the data, then it transmit to the the atmospheric modify the incoming and reflected radiation depicted with dashed lines in this figure passing through it. The Earth station, the satellite transmits the collected data to an Earth station represented by ground-based satellite dish. This is processed for the analysis at the Earth station. When Earth station process the data, we get this final image. This image is satellite image. You can see it in the figure. This is the processed image. We hide this 1 minute. Okay. This is the processed image on the right side of this is the false color composite. FCC. It is called FCC. False color composite images highlight features like vegetation, land use, or soil properties. The specific area, the area marked in yellow boundary is delineated using yellow boundaries for further analysis. Okay, understand? This is the how remote sensing technology or tools help in identify the earth features, yeah, objects. So these remote sensing studies concern particularly four soil parameters. Four soil parameters. What are the four soil parameters? First one is soil moisture. Second is soil surface roughness. Third, soil texture, and last one is soil temperature. If we talk how soil moisture can be identified using the remote sensing, so soil moisture, what is soil moisture? Soil moisture is a key parameter influencing the manner in which rainwater is between the phenomena of evapotranspiration, infiltration, and runoff. When soil has moisture, means it has some amount of water. When we want to capture soil moisture in remote sensing, then high soil moisture will reflect less EMR electromagnetic radiation compared to soil with have less soil moisture, less water. Soil surface roughness is involved in the separation of water flow into infiltration and runoff. Moreover, monitoring the evolution of surface roughness is a way to estimate erosion risk, particularly in agricultural area. Means soil surface roughness means soil which have high roughness is scattered more electromagnetic radiation and less energy captured by the sensor. If you talk about soil texture is one of the most important soil property influencing most physical, chemical, and biological soil processes. Hence, it is a key property for soil management. If soil texture is very rough, then the sensor receives very less EMR, and the images showed rough texture will be little bit scattered type. In rough type means. Last parameter is soil temperature. Soil temperature parameter is the description of evapotranspiration and surface atmosphere in the processes. Soil temperature also varies and can be identified with the help of remote sensing. When we get these four parameters, we can study the how remote sensing can help in identify the soil erosion and to prevent the degradation of the soil. Now we talk about the what is GIS. Geographical information system can help in the land to prevent the land degradation. Just I want to brief you the what is GIS. GIS is a geographic information system. Is a powerful tool for collecting, managing, analyzing, and visualizing spatial and geographic data. There are two types of data. That is the spatial and geographic data. So means GIS. In the GIS, we try to collect, manage, analyze, and visualize these data. GIS plays a vital role in understanding environmental processes and supporting decision making for land and resource management. In the context of land degradation and soil erosion, the GIS integrates remote sensing data with other geospatial information to monitor, assess, and model changes over time. If we talk, if we focus GIS for monitoring land degradation and soil erosion, GIS play a crucial role in several regions. Just for example, we spatial analysis for the soil, such as extent, severity of land degradation and erosion. Integration of data, in other terms, GIS combines from various sources such as satellite imagery, field survey data, and hydrological models. GIS helps in temporal analysis also. It tracks changes over time, providing insights into trends and effectiveness of the interventions. GIS can help in decision support also. GIS outputs such as maps and reports inform policymakers and stakeholders for sustainable land management. Means overall, if we combine all these, so GIS can help in many ways to monitor land degradation and soil erosion. If we talk what are the components of GIS, just as we studied the remote sensing components, if we take GIS components in this context, so there are two components. First one is data sources, second component GIS tools and techniques. If we talk about data sources, the first data we get from the remote sensing data, second data we get from the topographic data, third data, soil data, fourth climate, and last one is land use data. And we talk about the remote sensing data means high resolution satellite imagery. High resolution means the resolution of the imagery may be 5 meter, maybe 30 meter, maybe in kilometers also. And aerial photography for monitoring surface changes. In topographic data, we take the digital elevation model. I think all of you know what is the DEM, digital elevation model for understanding terrain and slope characteristics that influence erosion. We get the soil data by going to the field and taking a sample of soil and do the sieve analysis. Soil data attributes such as soil type, texture, and moisture content to model erosion susceptibility. In climate data, we get the data of rainfall and wind data for modeling erosion caused by the water and wind. In land use data, we have to collect information on vegetation cover, agriculture, and urbanization. The second part of GIS is the second component of GIS is GIS tools, raster analysis, vector analysis, overlay analysis, and spatial interpolation. We do not try to go in detail of GIS. Now we come to the next part. That is remote sensing and GIS for management of problematic soils. Means we combine remote sensing and GIS in this slide. When we talk about GIS paired with remote sensing is an indispensable tool for understanding and addressing land degradation and soil erosion. The both tools means remote sensing and GIS have the ability to integrate diverse data sets, perform complex spatial analysis, and provide actionable sites, makes it invaluable for sustainable land management. Actually, however, its success depends on the accurate data, robust model, and collaboration between the data and different scientists which are working on this field. If you talk about problematic soils, we categorize this problematic soil in three categories. First one is management of salt affected soils. Second category is management of eroded soil. And last category is management of assessment of droughts and floods. The first category is management of salt affected soils, mean soil which has some amount of salt. Salt means uh, as you have you visited visited Gujarat, Kutch area? There is salt affected soil too much. A wide variety of satellite remote sensing data from multi-temporal landscapes are now available to earth resource scientists generating information for detection of spectral salinity in the soil. The combination of remote sensing and the GIS are used for variety data to delineate salt-affected soils. The most commonly used techniques for a salinity index is the computation of different indices and rescue images using infrared and visual spectral bands. Means to identify the salt-affected soils in any area, bands, different spectral regions. Yes, we get the one image in the infrared region and get the different same area in different band means in visual spectral bands. After getting both images, we analyze and trying to find out what area is affected by the which area present. The second, management of eroded soil. The potential utility of remotely sensed data in the form of aerial photographs and satellite sensors data has been well recognized in mapping and assessing landscape attributes controlling soil erosion, such as physiography, soil land use, land cover, relief, and soil erosion pattern. In this sector, remote sensing can facilitate studying the factors enhancing the process, such as soil type, slope gradient, drainage, geology, and land cover. So then, multi-temporal satellite images provide valuable information related to the seasonal land use dynamics. In this case, satellite data can be used for studying erosional features such as gullies, rainfall intersection, vegetation, and vegetation cover factor. In this, one of the vital inputs required for soil erosion modeling can be created by analysis of stereoscopic, optical, and microwave remote sensing data. The last one is assessment of droughts and flood. Drought prediction can be benefit from climate variability predictions using coupled ocean atmosphere models, survey of snowpack, persistent anomalies, circulation pattern in the ocean and atmosphere, initial soil moisture, assimilation of remotely sensed data into numerical prediction models, and amount of water available for irrigation. Remote sensing for floods is used in storm scale using hydrodynamic models by monitoring the intensity, movement, and propagation of the precipitation system to determine how much, when, and where the heavy precipitation is going to move during the next 0 to 3 hours. And the last is hydrological cycle is precipitation, rate and accumulation, moisture transport, and surface soil wetness. Means by doing all these three techniques, we easily identify and get the solution for any problematic soils in any area. After getting the problem, we collect the soil inventory, means soil resource inventory. So it's a key role in the management of natural resources because management of soil resources on scientific principle is essential to maintain the present level of soil productivity and to prevent soil land degradation. In this, mapping of different kinds of soils and developing regional and scientific criteria for land evaluation and interpretation of soils like multivariate land uses. In soil resource inventory, remote sensing technology is found to be more efficient and economical than the conventional methods. GIS and remote sensing is a powerful and sophisticated tool for displaying and analyzing spatial relationship between geographic phenomena in the form of vectors and images. Many researchers, as you know, that conducted several experiments and found out the potential of remote sensing and GIS in soil inventory and resources. The synoptic and repetitive coverage of satellite over large areas, remote sensing techniques have reduced the field work to a considerable extent, and soil boundaries are more precisely delineated than in conventional methods. As you see in this image, the left side image shows the less number of samples collected by the field survey, and in right side there are huge number of samples collected during the field survey. Aerial photographs were being used as a remote sensing tool for soil mapping. These aerial photographs and satellite data, both digital and analog forms, have been utilized for preparing small-scale soil resources maps. During mid-80s, Landsat thematic maps and IRS lift second data were used by the scientists to map soils at the scale of 1:50,000, and at this scale, soil could be delineated at association of soil series or a family level. There are Indian remote sensing satellites also like IRS-1A, IRS-1B, 1C, provide state-of-the-art database for natural resource inventory. If we combine all this and want to know what is the role of remote sensing in land use study, before going into detail, I want to clear what is land use land cover. There is little difference between land use and land cover. Land use is the how the land has been modified by human activity, such as agriculture, forestry, and urban development. And land cover is the physical process of the earth, such as vegetation, water body, and bare soil. I am repeating. Land cover is the physical surface of the earth, such as vegetation, water body, and bare soil. Means If there is no disturbance, there is no human intervention in vegetation, then it is land cover. We go and disturb the vegetation and make it forest, use this land cover as agriculture, then it will becomes the land use. So land how can be modified by human activities is land use. Means land and land cover is a way to classify the physical and functional characteristics of the earth's surface. In short form, this land use land cover will be called LULC. LULC maps are created using remote sensing images and machine learning algorithms. They LULC help people to understand how the land has been changed over time and how human activity and natural processes impact the environment. Initially, all area is as a land cover, and when human intervention in that area, that will become the land use. So why land cover maps are so important in the assessment of soil erosion and land degradation? So these maps are prepared for policy and land management because these maps help and inform decisions about the sustainable development, environmental management, and smart city planning in the nowadays. These agricultural maps can be used to monitor change in agricultural ecosystems, forest conservation, and surface water body conservation. These agricultural maps help people understand the impact of natural hazards. Want to know what is land use land cover? Then we get the information that how land cover is converted into land use. Information on the existing land use and land cover pattern and its distribution is a prerequisite for better understanding of land aspects and also plays a vital role in development planning. With the advent of remote sensing techniques, both aerial and satellite, it has been possible to prepare land use maps at various levels, showing categories of land under different uses, both in spatial and statistical form. The FCC of thematic mapper, FCC's false color composite of thematic mapper data were used for identifying and delineating wasteland. Wastelands were identified and mapped on a scale of 1:25,000, compared land use land cover change of watershed using remote sensing and GIS data, which made an attempt to study the change in the land use pattern. What is land use and land cover? Now we go to the case study, move to the case study. In this presentation, we take a case study of Sipra River Basin. Sipra River Basin situation. Okay. So before going doing that, we prepare a watershed of a Sipra River. Now I want like to explain what is watershed. Watershed is a natural area which contributes runoff to an outlet point. Okay. So it can be classified according to the density of area. So naturally, watershed is an ideal unit for management of natural resources. Natural resources like land and water, and for mitigation of the impact of natural disasters for achieving sustainable development. This is the drainage basin. As you can see that this red part is the red line is called the ridge line, and all area covered this under this area is called basin या फिर watershed. So drainage basin is a land area that drains water from rain or snow melt into body of water. It includes the land surface, streams and rivers that carry water. So the features of this drainage basin can be understood. That is watershed. Watershed is highland area that surrounds the drainage basin. There are tributaries. Tributaries can be main tributaries and the subsidiary tributary. Tributary is a small river or a stream that flows into a large river. Confluence. Confluence is a point where two rivers meet. Means where two rivers meet. Yeah, when two tributaries is meet. And the source. What is the source? The source is the beginning of a river. From the river it originates is the source of that river. And the last where the river departures, yeah, the point where a river meets the lake or ocean is called the mouth of that river. These are the main features of the drainage basin. If we want to know the examples of drainage basin, we can understand that the Amazon River Basin is the world's largest drainage basin. And another example of drainage basin is Mississippi River Basin, which covers almost 40% of the 48 states of the America. Now we take the problem statement. What is the problem in this case study? As the soil, as you, all of you know that soil is renewable natural source, yet it can become finite with the passage of time through its degradation. In Sipra River Basin, soil degradation is a problem, and there are several causes for this. To identify which area is the most susceptible to the soil erosion, we do this case study using the remote sensing and GIS. Okay. Now these are the four objectives of this study: to analyze the morphometric parameters of Sipra River Basin, prepare LULC, land use land cover map, and on that basis find out the priority. Priority means what? In terms of which area is most susceptible to the soil erosion. Then we do this exercise with the help of another method. That is method is USLE, Universal Soil Loss Equation. Means in the next step, we estimate the soil loss in Sipra River Basin using Universal Soil Loss Equation with the help of rainfall data, dam, soil property, and land use land cover. We will discuss in detail in the next slides. In the last, we combine all three methods. First method is morphometric parameters. Second method is land use land cover map. Third method is USLE. And in the last, we integrate all three methods to identify the actual condition of Sipra River Basin, that this means north side, south side, east or west side, which side is the most susceptible, yeah, most highly susceptible to the soil erosion. And on that basis, we recommend that to prevent this soil erosion, we recommend some structures to install at that places. This is the study area, Sipra River Basin. The Sipra River Basin, the latitude and longitude of that basin is as shown in the figure. If we talk about the overview of the study area, Sipra River Basin, also known as Avanti Nadi, it originates in Vindhya range and flows in a northerly direction across the Malwa Plateau to join the Chambal River. This River Basin, the Sipra River is a river of religious importance in Madhya Pradesh state. Total length of the river is 195 km, out of which 98 km flow through Ujjain. The catchment area of Sipra River Basin is 5,600 km square. The main tributaries of Sipra River include the Khan River near Ujjain and the Gambhir River near Mahidpur. The climate of Sipra Basin is semi-arid and receives an annual rainfall of about 1,400 mm. This is the distal elevation model of the Sipra River Basin. You can see that minimum elevation of this area is 406 meter and the maximum elevation is 773 meter above mean sea level. Means the this side, north side of the Sipra River Basin is have lower elevation. That is minimum elevation is 406 meter, and south side had the highest elevation and maximum elevation is 773 meter. These are the basic parameters of that study area. Now we go to the data used in each and every study. First method is morphometric analysis. In analysis of morphometric analysis, we use SRTM DM. This is the detail of the imagery which was used in this study. And the second data used is Survey of India toposets. In this study, we use toposets. Number is 46 m by 10, 46 m by 11, and the scale of that toposets 1,500. 1 to ratio 50,000 scale. For the analysis of the land use land cover analysis, we used this data, Landsat 5 data, thematic mapper sensor, okay, and in 6 different bands. 6 different bands. This is the data required date on which the image satellite has captured the image of that area and the raw and path of that satellite imagery used in this study. The third method, land use land USLE method. In this, we take the data from IMD, Indian Meteorological Department, and some data has been obtained from the India Water Portal, and another data is required is soil map. So means in this you can see that we utilize maximum data from the remote sense data. Means in morphometric we use SRTM and Survey of India. In land use land cover we use Landsat 5 thematic mapper, and in USLE method we use meteorological India water and soil map. So just I want to show you how we can download the remote sensing data from the USGS website or any other website. Just go to the Google and type the Earth Explorer. Go to the Google and type Earth Explorer. The first link which comes out is the earthexplorers.usgs.in.gov. The first link will be available in the earthexplorer.usgs.gov. Just click on this link. You get this page. This page is developed by USGS. In this page, you can see that this image, this is the US. We type the feature and get the satellite image of that area. Just for example, we type Lucknow. We get results are loading and we get this Lucknow. This place is shown in the Minnesota. We type in Lucknow, India. Now we type Lucknow, India. Results are loading, unable to find out. Just a minute. Word features, select word features. Lucknow, India. We get the result, but it should be unable to locate. No issue. When we get the data, when we get the this website, go to India, minimize it. This is the empty. We take the this area. Okay. Then go to the data sets. Go to data set. Here are you can see that there are so many satellites are available. Aerial imagery, AVSHR, ELOS. We go to the distant elevation. We go to distant elevation. And then SRTM. We get SRTM 1 and go to the result. When we go to result, we can see that there are so many options are available. This is the date on which this image has been acquired. Yeah, this image has been published. That is 23 September 2014. Similar other images are available. We get the download, the link, and the file is ready to download. Okay. By doing this, we get all this data from the Earth Explorer, USGS Earth Explorer. Okay. Now we go to the methodology of each and every method. First methodology. First we discuss the methodology for morphometric analysis. This methodology can be divided into two segments. First one is extraction of the stream characteristics for watershed as well as sub-watershed. We prepare the watershed for Sipra River Basin and then it categorized into sub-watershed, small sub-watersheds. So for the delineation of the study area means delineation of the Shipra River watershed, we use SRTM Sink Free Dam. Already shown in the figure 1. So with the help of outlet point and by using watershed tool in the ArcGIS software, we delineate study area. One more point I would like to discuss that the GIS part will be done in ArcGIS. ArcGIS software is a licensed software. We have to purchase it. But for research purpose, you can use QGIS software. QGIS is a open source and free software and a very small software. You can download it directly from the website. Then we use watershed tool in ArcGIS, या फिर otherwise in QGIS to delineate the study area. After that, extraction of the drainage network has been done using the flow direction tool, flow accumulation and stream order. We get the flow direction map when we give the command to the software and we get this result. Flow direction map is a raster data set that represents the direction of water flow across each cell of the grid. Means in this, when we zoom this figure, we get that the where flow of direction has been flow direction in this direction, often used in the hydrological modeling and GIS to simulate water movement, calculate watershed boundaries, and analyze the drainage network. After getting the flow direction map, we find out to flow accumulation map. So this is the raster that shows the accumulated flow in each cell. Means in each pixel means when we zoom this raster file, we get a small square that is called pixel. So when in flow accumulation map, we get the how much amount of water accumulated in that pixels. So this flow accumulation map can be used to identify the stream channels. These accumulation flow maps can also be used to identify the ridges. Ridge is the boundary where water cannot transfer from this side, left side or right side to other side. So this flow accumulation map can be used to determine how much rain has fallen within a given water set. Okay. After the flow accumulation map, we prepared a stream order map. Stream order map is the method of assigning a numeric order to link a stream network. Means in this stream order map, we assign a numerical value to each and every stream. In stream order map, we assign the numerical value to each and every streams. Means main stream get the highest value and small streams get the lowest value. To ordering the streams, there are two methods. First method is installer order system and second method is Sri magnitude system. In installer order system, we designate the streams by first order and the second order streams will be designated as plus 1 means a plus 1. If we just for example say both of its branch stream have the same order a, then the order of the link will be a plus 1. While in the stream magnitude system, the joint stream will get the same number of orders. In case of two tributaries have different orders, means one tributary has the order of 1 and second tributary have an order of 2, then the third tributary which joins the both tributaries will get the order of higher order means 2. But in the three magnitude system, we get the 2 plus 1, 3 will be the final output order. Means after preparing the stream order system, we use stellar order system. Generally, in our case, we use stellar order system and we get the stream order map as you shown in the figure. After preparing this map, we prioritize these sub water set into 43 different parts. Means we categorize this Chipra River basin into 43 parts and arrange this in this category based on the soil erosion susceptibility. This is the subwater set 43 and for each subwater set means for all 43 subwater set we calculate some morphometric parameters. You can use it Excel for calculation and we category calculation can be categorized into two parts. First one is linear parameter and second is shape parameters. In the linear parameters, there are five different parameters. First one is drainage density, stream frequency, bifurcation ratio, drainage texture, length of overland flow. While in the shape parameters, there are five parameters: form factor, circulatory ratio, elongation ratio, compactness coefficient, and basin shape. So for all 10 parameters, we have some fixed formulas given by some scientist. You can see from the table that a stream order formula has been given by the Strahler. Steam length formula has been given by the Horton in 1945. Mean steam length formula is given by Strahler in 1964 and the formula is LU upon NU. LU is the length of stream and NU is the number of streams. Similar other formulas has been given by different scientists in different time duration and we calculate these parameters for each and every sub-water set. Means we do this exercise for all 43 sub-water sets. Understand? We prepare a table. After calculating all parameters, we just skip. We prepare a table like this. Okay. There are sub-water set. There are 43 sub-water sets in the left side of the table. And number of streams order wise means in first order sub-water set, there are 359 streams of first order, 90 streams of second orders, 27 streams of third order, 2 streams of fourth, and 1 stream of sixth order. Overall, there are 479 streams in the sub-water set of 1. Okay. Similar, we calculate these number of streams order-wise in all the 43 sub-water sets. Understand? When we get this data, we calculate the value for each subwater sets and stream length and other parameters. Means in the second slide, second table, we get the stream length order wise for all 43. Means just for example, for subwater set 1, there are 238.9 kilometer length of first order stream, 110.933 kilometer of a second order streams, and overall 465.14 kilometer total stream length. You can imagine the data. This data has been prepared using the GIS. Okay. Now, when we get the stream number of streams and the stream length, we calculate other parameters like area of that subwater set, perimeter of subwater that subwater set, basin length, minimum elevation, maximum elevation, and total relief. Total relief is the difference of minimum elevation and the maximum elevation. Means it is the difference of 497 and 413 for subwater set 1. This is the basic parameters. After calculating the basic parameters, we calculate the other parameters, that is linear parameters and shape parameters. We calculate the mean bifurcation ratio for each water set, and this is the table which shows the linear parameters and shape parameters. These parameters are calculated based on the formula as in the previous slide, formulas given by the different scientists and researchers. Means if we talk about the drainage density for subwater set 1, it comes out to be 0.16. Similarly, for different subwater sets, we get the these values. After getting these values for each subwater set, we prioritize these subwater sets based on their condition of the soil, based on the soil erosion condition, soil susceptibility. Okay, understand? In this slide, we provide the priority to each and every subwater set. This table shows the own value according to the values of various morphometric parameters. Okay, so this is the map, final map which we get from the GIS, which shows the subwater set number. Higher number shows the that subwater set is the highly susceptible to the soil erosion. By this, we can identify that, just for example, in this case, Sipra River Basin subwater set number 1 shows the least erosion, and subwater set number 43 shows the highest erosion. Okay. Now we do this exercise by another method, that is land to land cover analysis. Means you understand, all of you, that in the first process we we prioritize the all 43 subwater sets using morphometric analysis. Now we do this exercise by using land to land cover. As all of you know, we assign the land to land cover prepare based on the tone, texture, pattern, shape, size, shadow, and site association. And based on that, we calculate the agricultural land, habitat, built up area, and all area categorized for each and every subwater set. According to the area of each class in each subwater set, rank 1 was provided to the that subwater set which has lower area, second highest area as rank 2 and so on. After providing rank to each subwater set for particular class, compound values are calculated by averaging the rank of 4 classes. We go to the table. As you can see that from the table, subwater set 1 has the barren land of 43 kilometers square, forest land has 28 kilometers square, dry land had 38, land vegetation 4, and compound value is 28.25. And based on these values, we provide the priority of each and every subwater set. Now we get this figure after prioritizing the subwater set based on the land use land cover. In this figure, as previously figure, we get the almost similar results that shows the subordinate one is at the 28th rank. Now to find out the how much soil is eroded means quantification of soil is done based on the universal soil loss equation USLE. So universal soil loss equation is an attempt to predict the soil loss from smaller areas. This is developed in 1962 by United States Agricultural Research Services. In this, they provided a empirical formula that is A equal to R into K into L into S into C into P, where A क्या है? A is average annual soil loss in tons per hectare per year. R is the rainfall erosivity factor. K soil erodibility factor. We will discuss all these factors in the next slide. L is slope length factor, S is slope steepness factor, C is crop management factor, and P is conservation support practice factor. After calculating the value for each parameters, we multiply all the values and get the annual average annual soil loss. Unit of that is tons per hectare per year. Okay. Now we talk about the rainfall erosivity factor. As all of you know that if any area gets the heavy rainfall, the chance of erosion may be bigger and higher. If any area get the small rainfall, the chance of erosion will be less. Based on that factor, this soil rainfall erosivity factor has been developed, and it only depends on the amount of rainfall, amount of precipitation comes over that area. To calculate this rainfall erosivity factor, a formula was given by Wismar in 1959. That is R equal to P into 0.5. Means if we multiply the amount of rainfall by zero point 0.5, we get the rainfall erosivity factor. Here P is the mean annual precipitation in mm. So for doing this, we collect the rainfall data at 7 stations, and the location of that station is shown in the table, and we get this value of precipitation for these stations. Means for Indore, we get the precipitation value 750.887 mm. In Jan, we get the value of 864.283. In August, 754, and like that. We multiply this value by the factor in 0.5 and get the rainfall erosivity factor, and prepare this map on the QGIS or या फिर ArcGIS. Rainfall erosivity value map. From this figure you can see that the dark blue area means south part shows the high erosivity factor. Okay. Now for the soil erodibility factor, there is another formula given by Wijmar in 1961, and the formula it is little bit complex, and calculation of this formula can be done in the Excel, MS Excel, or in other software. This formula represents K soil erodibility factor. M is the percentage silt, silt percentage quantity, and A percentage organic matter content, B is soil structure code of the soil, and C the profile permeability class of soil. For calculating the soil erodibility factor, we do the sieve analysis and at some places and get this value for soil erodibility factor. Okay, for this study area, we take the I think 20 samples and prepare the soil erodibility factor. In the soil loss equation, slope length is defined as the distance from the point of origin of overland flow to the point where either the slope gradient decreases enough that deposition begin or the runoff water enters a well-defined channel that may be part of the drainage network or a constructed channel. This can be calculated as lambda upon 2.13 ki power whole power small m, where m is the dimensionless exponent depend on the slope steepness. Value of m will be 0.5 for slope is steep exceeded 5%, and its value will be 0.4 for slope exceeds 4%, and so on. The second factor is slope steepness effect. The surface water runoff from the water set increases as slope steepness or say gradient increase. As you can visualize this slope steepness effect, as the slope will be steep, the erosion will be more. This will also affect the erosion, soil erosion, increase the land degradation. For this calculation, there is formula as equal to 10.5 sin theta plus 0.03 for slope is less than 9%. If slope steepness is greater than 9%, then this formula will become as equal to 16.8 sin theta minus 0.50 for slopes greater than or equal to 9%. In combined form, both terms called topographic factor. Okay. The another factor is the crop management factor. This factor can be calculated C equal to exponentially minus gamma bracket ndvi upon beta minus ndvi bracket close, where ndvi is the normalized difference vegetation index. It's an index that is calculated based on the bands, different bands, and gamma and beta are the dimensional length parameters. Then for this study, we prepare these maps, NDVI map of the Sipra River Basin, and the value of these maps will vary from minus 0.68 to 0.75. And this is the another figure in the right side is the crop management factor prepared on the RGIS. Now combine all these values and conservation support factor, we get the final value of the soil erosion. This is just a flow chart to analyze to find out the USLE equation means rainfall data, R factor, rainfall R factor, soil maps, soil characteristic taken, and K factor is calculated. NDVI maps, from NDVI map, we get the pure soil vegetation pixels and C factor is calculated. LULC maps, land cover and P factor calculated, and depth and contour from this we get the L and S factor. Now combine all these factors, multiply and get the soil loss potential. Then this table presents the value for each subwater set. Means if you talk from the for the subwater set 1, R value is 426, K value is 0.189, LS value is 12. Similar on that. The final priority will be based on this value. We prepare a map of this based on the USLE analysis. Okay. Now combine all these methods, integration of the results, and we get the more accurate result compared to the individual results. You can see that subwater set 1 get the 20th rank from the priority morphometric method, 18th rank from the IULC method, and 25th rank from the USLE method. You can see that for subauto set number 26 get the second rank in the morphometric method, 28th rank in the LULC, and first rank in the USLE method. Similar, the subauto set number 28, 28 get the first rank in the morphometric, first rank in the LULC, and 8th rank in the USLE. We can say that the subauto set number 28 is the highly susceptible to the soil erosion and soil conservation structures to be installed in this place immediately. This type of study will suggest that how we can stop, yeah, how we can minimize, yeah, how we can regulate and control the soil erosion, yeah, land degradation in that area. This is the pictography figure for that area. That part shows the severe affected area from the soil erosion. Means the south part of this study area has severely affected from the soil erosion, and the north side has the less affected or not affected from the soil erosion. This is the integration of the three methods. Okay. So now we talk. Now I think it's a clear representation of each sub-water set for this study area for this Sipra River Basin. And by observing or by looking at this figure, we can easily demarcate, we can easily understand that on which area we have to install structures to prevent or to control this soil erosion. So for future scope and recommendation, that stormwater modeling can be done with the result and integration of this modeling with the morphometric analysis with the groundwater level data for piezometric stations can be very helpful in assessing and locating the groundwater potential zone also. Okay. The present study demonstrates the utility of geomatics, it means remote sensing in GIS in prioritizing subwater set, which may be helpful to water resource planners and decision makers. Okay. Now, after getting the area, after identifying the area which are highly susceptible to the soil erosion, what are the soil and water consumption structures to be installed here to be suggest to policymakers, yeah, researchers to prevent this? Just for example, we in the table we elaborate a type of conservation structure and criteria to be followed. If you provide contour bunding, the slope of that area will be level to medium, and soil texture will be low, and a small to medium watershed area runoff potential will be medium. For gully plug, level to medium ground and very low soil texture. Similar Nala band medium watershed level to gentle slope, medium soil texture, and medium runoff potential. So by providing these type of conservation structures, we can prevent or minimize the soil erosion or land degradation in that area. I think we implement all these methods in a good manner and provide you the brief insight how remote sensing in GIS can help in monitoring the soil erosion or land degradation. Okay, so thank you for joining on this journey. And have you any question? Now move to the question answer session. Hello.
Yes, sir.
Now can we move to the question answer session? I think.
Yes, sir. I request all the participant, if you have any question, you can post in the this chat box, and sir can answer from there. Please.
All of provide the introduction part only. No question is here.
Any question, please? I guess, sir, there is no questions.
Okay, no issue.
One thing I will do, I'll just, allow all the participant to unmute themselves.
Okay, okay.
Uh,
One question is a soil mapping.
there is one question.
What is the question is a soil mapping means? Are you want to do a soil mapping? Sir, any insight with soil mapping? It depends on the user's perspective. What purpose you want to soil map? Geotechnical properties of soil. Uh, Remote sensing can provide the just initial information about the soil. Means for getting the just for example, you want to texture of that soil. You want to detailed analysis. For this you have to do sweep analysis. Remote sensing cannot help in detailed property to get the detailed property of soil. Remote sensing only provides the initial information about the soil mapping, that this soil may be little bit have moisture, this soil have no moisture, but if we want to quantify the what amount of moisture the soil have, so then we have to go to the field and take the sample and uh, take the compaction ratio and found out the soil moisture ratio. Second question is, can calculating catchment area using AI? Now, this licensed software, that is ArcGIS, has inbuilt tool to calculate the catchment area. There is a tool catchment. We give the input and click the tool, and it automatically demarcate the catchment. And by doing this providing the command, we get the directly area in meter square, kilometer square. or you can also program in the QGIS to do this. But licensed software has a tool to calculate catchment area directly. Okay. Next.
I have allowed all the participants to unmuted them, so they can ask any question. Otherwise, we can end this session.
Excuse me, sir.
Yeah.
Yes, yes.
Sir, can soil erosion be monitored using the remote sensing techniques, sir?
Yes, yes, sure. For monitoring, we have to take the multiple data. Means if we take the data of 23 January 2025 of any particular area, we take the image and save it. Then after 10 days, yeah, after 15 days, we take the another image of that area, same area, and we compare both pictures, both satellite images, and we want to check that if there is any change in that area, then we go to the field and check the area. What is the possibility of that change in that area? If there is no change, then there is no soil erosion.
Okay,
Okay,
sir. Similarly, flood
means
mapping can also be done, right, sir?
yeah, flood mapping also be done. Soil erosion, any change means just for example deforestation study. Deforestation study can also be done in remote sensing.
Okay, okay, sir. Thank you very much.
Can you explain in detail about the DM? Digital elevation model is just so the top surface of the earth. Means in the DEM model we get the in the pixel value we get the what is the elevation of that feature that object from the mean sea level. Just for just for just for example, if we get the dam of Lucknow area, yeah, like some other area, so we get the in each pixel we get some value, and that value represents the mean height of that particular feature from the mean sea level. How to identify soil classes and image? To identify the different soil class, we get to high resolution satellite image. In high resolution satellite image, we easily identify the soil class in different categories. In coarse resolution image में, we cannot identify the different soil classes. Okay, Santosh ji?
Sir, similarly, water quality changes in the sea or in the lakes. Can this be monitored using remote sensing techniques, sir?
Right now, water we can easily identify that water is polluted or non-polluted, but to quantification is not possible through the remote sensing. We can just tell to anyone that this water is polluted, this water is fresh. But if someone asks that how much pollution is there, what are the parameters is there, that is not possible through the remote sensing. For that,
Okay.
we have to take sampling.
Okay, sir. Yeah, fine, sir. Thank you, sir.
Okay, thank you.
Hello, good evening, sir.
Good evening.
Sir, how can satellite imagery help in assessing soil erosion?
For assessing soil erosion, you get two different satellite imagery of different time duration, and by comparing, you get the uh, assessment of soil erosion. Two different imagery at two different time, and comparison of that imagery, you get the solution of this answer.
Okay, sir. Thank you, sir.
Okay, Midhuri?
Okay, sir. Uh, Padam sir, thank you so much.
Thank you, sir.
It was so wonderful session from your end. I have seen all of your PPTs. It was so enriching session, and actually I also from the GIS background, so it
Okay,
was
okay.
yeah, it was enriching for me also because I have added so many knowledge from your PPT. So thank you once again on the behalf of BIT as well as ATAL FDP for accepting our invitation and for being here. It is truly pleasure for us, and I hope some more sessions from your side in coming future. And if possible, please visit to our institute for more sessions like this. Thank you, sir.
Okay, sure, sure. Thank you. Thank you.
Thank you. Dear participants, we'll start the next session after 5 to 10 minutes. So we can take a break then.